Welcome to This Explainer. Today, we're diving into a topic that forms the absolute backbone of literally any major commercial or industrial build, yet it's kind of misunderstood until things go wrong. Cable tray installation. But what's really fascinating in our sources today is the mindset shift. We're going to look at this entirely from the perspective of a senior installation engineer. We're going to see exactly how veterans analyze routing and planning, shifting the whole job from reactive labor to proactive control. Let's jump right in. So, let me hit you with a harsh truth, straight from the field. Most cable tray installation problems trace back to decisions made before the first bracket is drilled. When a massive cable pull goes terribly wrong, or a tray physically buckles under the load, the immediate instinct is to blame the materials, or the crew pulling the wire. But the veterans? They know the truth. That failure was actually baked into the project weeks ago on a drawing board. The stakes here are incredibly high, because structural failures are dangerous, and reworks will absolutely tank your budget.
All right, Section 1. Before the first bracket. Avoiding disaster before drilling. Our sources highlight an incredible contrast in how people approach this pre-installation phase. Take the rookie method. A rookie gets to the site, they want to show immediate progress, right? So they grab a hammer drill and start throwing up brackets, figuring they'll just check the spans and cable loads later. Now contrast that with the veteran method. A senior engineer stands back. Their tools stay in the box. They're mentally building the entire system first, checking the segregation of power and data, visualizing clearance around HVAC ducts, and making sure there's actual physical access for the electricians later. They coordinate the route first because they know putting metal on a wall is the easy part. Putting it in the exact right place, that's the real job.
Moving to Section 2, the 6-point route checklist, the proactive foundation. To get this right the first time, you absolutely need a strict framework. Let's walk through this checklist, because doing this math is what separates a safe site from a total disaster. First, coordinate all routes. You've got to cross-reference your tray path with plumbing, HVAC, and drywall to avoid clashes. Second, verify segregation. You cannot run high-voltage power lines right next to sensitive data cables without physical barriers. Otherwise, you're looking at massive electromagnetic interference. Third, check your clearances, because these trays need breathing room to dissipate heat. Fourth, confirm stacking order. Heavy power goes low, lighter telecom goes high. Fifth, plan access spacing. Have you ever tried pulling thick, rigid armored cable into a tray that only has 2 inches of clearance above it? It is a total nightmare. Leave room for hands and tools. And finally, the golden rule, hold off on drilling until all of that is verified.
Section 3. Deflection math and cable loads. Proving why the blueprint matters. Okay, once your route is clear, we step into the actual physics of the job. At the end of the day, cable trays are at the mercy of hard math, not guesswork. The crucial thing to understand here is the deflection limit, specifically L/200. This is your structural threshold. It essentially means your tray cannot sag more than the span length divided by 200 when fully loaded. When you have a span between two brackets, gravity is relentlessly pulling down on that metal and the heavy copper inside it. Ignore this calculation and you end up with a sagging tray. And look, not only does that look completely unprofessional, but it stresses the cable joints and ruins the integrity of the whole system.
Let's put this into perspective. Say you've got a cable load of 40 kilograms per meter and brackets spaced at a 3.0 meter span length. Your deflection status is totally safe. But what happens if the project scope suddenly changes, routes get combined, and your load doubles to 80 kilograms per meter? If you keep that exact same 3-meter span, boom! You push right past the L/200 limit. The system fails. A veteran engineer catches this immediately. They see that 80-kilo load and know, for sure, they need to reduce that span length, maybe moving brackets that every 1.5 or 2 meters.
Section 4. 5-step site installation sequence. Hitting the field.
So, the route is perfectly planned, the math is triple-checked, now we execute. Following this exact sequence is how you translate that perfect blueprint into the real world. Step 1. Marking out the route. Use lasers and chalk lines to map the path on the ceiling based on your plan. Step 2. Placing supports and brackets. Here's where the drilling finally happens, securing anchors for the loads we just calculated. Step 3. Tray assembly. Bolting the straight sections, bends, and tees onto the brackets. Step 4. Cable pulling. The electricians come in, laying cables smoothly without dragging them over sharp edges. And lastly, Step 5. Bonding. You have to ensure the entire continuous metal system is grounded to electrical earth for safety. Stick to the sequence. Mixing these steps up is just asking for trouble.
Finally, Section 5, Hidden Variables and Compliance Standards. What separates the pros?
As any veteran knows, the job site is never perfect. Even with a flawless plan, curveballs will mess with your calculations. An installation is rarely just an open metal basket, right? Think about adding covers. They protect cables from debris, sure, but they also trap heat, meaning you might have to derate the cables or upsize the tray. What about fire barriers? When a tray passes through a fire-rated wall, it gets packed with intumescent material, which completely flips your access and routing dynamics. And then there's integrating EMC accessories, which demand specific grounding distances to prevent data corruption. A real pro is constantly dynamically managing these variables because they instantly shift your span and fill decisions.
And to navigate all these variables safely, you absolutely have to use compliant equipment. You can't just bend some sheet metal and hope for the best. That's why major manufacturers like Xinma are so crucial here. Their cable tray systems and busways are built to meet incredibly strict international standard bodies. We're talking IEC 61537, North America's NEMA VE1, the European BSEN 50085, and the Chinese GB 31251 code. When your equipment genuinely meets these standards, it gives the installation engineer the absolute confidence that their deflection math will hold up in the real world.
Well, we've covered a ton of ground today, from those early pre-planning checklists and deflection math, right through to field execution and global compliance. And it all circles back to that veteran mindset of proactive routing control. So, I want to leave you with a final thought to mull over regarding your own practices, whether you're designing the system or actually standing on the ladder. Ask yourself, is your next bracket placed by habit or by calculation? Keep that in mind before you reach for the power tools. Thanks for joining me on this explainer. Keep planning, stay safe out there, and I'll catch you next time.